Yeah. Hello, everyone. It's a pleasure to have Lea today, who will be telling us about gapped phases and phase transitions from the SymTFT. Please take it away, Lea.
Okay. Thanks a lot for inviting me to speak to this nice seminar series. And today I'm going to tell you about gap phases and phase transitions using the Symmetry TFT. And this is based on these three works that came out recently, which are in collaboration with Laksha Barwaj, who's a postdoc in Oxford, Sakura Sheffer-Nameki, who's my supervisor also in Oxford, and Daniel Payer, who's a student also in Oxford. So the framework in which we want to sort of fit this work is the standard Landau paradigm. And so Landau paradigm is a very old theory and well established that tells us that all continuous phase transitions are spontaneous symmetry breaking transitions. So the usual picture is that we have a theory with some symmetry S, and suppose that this symmetry may be spontaneously broken in some phase, which I call phase one, and preserved in another phase that I call phase two. And then there is a conformal field theory that interpolates between the two and sits at the transitions between these two phases. And moreover, we can characterize which phase are we in by looking at order parameters. So these are operators that are charged under the symmetry. And for example, an operator O that typically has a non-zero VAV into some order phase. So it condenses in the order phase, and it has instead zero VAV in some disordered phase where the symmetry is preserved. So the goal of this work is to kind of generalize this picture to what we can call the categorical Landau paradigm. So try to extend it in the case where the symmetry S, which characterize our phases, is not a standard vanilla group-like symmetry, but it's a symmetry that is described in general by some higher fusion category. Okay, and so the first disclaimer is that I will focus only on S, which is a finite symmetry, as is typical in this category business. And in particular, this means that I'm not going to consider spontaneous breaking of continuous symmetries and such. So there are no Goldstone bosons, and the IR phases that I will consider are always gapped infrared phases. And I will also strictly focus on 2 dimensions in this talk. So, okay. And as I was saying, the idea is to explain a setup to study gapped phases with symmetry S, and eventually also study possible phase transitions between these phases. And the key ingredient that I will use is the symmetry topological field theory, or SymTFT. So the plan is that I will start with a review of the SymTFT. It will be quite brief since I expect that most people are already quite familiar with it. Then I will explain how we can use the SymTFT to classify gap phases. This is what we explain in these 2 works. And then I will move to phase transitions, and so gapless phases. And we will see that discussing phase transitions will require us to extend the standard SymTFT picture to something that we call the club sandwich. I canceled my... to something that we call the club sandwich, and this is what we discussed in this paper from December. And then I will conclude. So, and throughout the talk, I will try to illustrate the main points with 2 examples. The first one is a symmetry Z4, which is a vanilla group-like case. And then I will move to a non-invertible example, which would be, is gonna be rep S3. Okay. And of course, the study of two-dimensional theories, both gapped and gapless, has a very long-standing history. So there are already a lot of works that discuss topics that are related to what I'm gonna talk about. So I tried to put in this first slide some of the related references. And I apologize in advance if I haven't cited all the related work, but essentially these first works discuss the topic of categorical symmetries in two dimensions, and also how we can use categorical symmetries to constrain gapped phases in the infrared. Then there are also works that discuss this one, more specifically gapless phases, and also phase transitions. In particular, this paper is, these two papers have a setup which is quite analogous to what I'm gonna discuss, but mostly focused on the group examples. And then there is also a huge literature on the SymTFT, which is the main tool that I'm gonna use. So these are some of the references. And also, a lot of these topics have also been discussed, not from a continuous perspective, but on the lattice. Okay. So let me start now with the Symmetry TFT. So the starting point, so the input to construct the SymTFT is a two-dimensional quantum field theory T, which has a global symmetry S. And I stay in 2 dimensions. So the symmetry S is just some standard vanilla fusion category of topological line defects that represent the symmetries of the 2-dimensional theory. And what the Symmetry TFT is that it's a 3-dimensional theory, topological, Z of S, which is essentially the Turai-Viro theory based on S. And the property of the Symmetry TFT is that my original 2-dimensional theory T can be recovered as the interval compactification of the SymTFT with appropriate boundary conditions, which I'm gonna discuss. So also in the 3D bulk, so in the 3D topological field theory, which is the Symmetry TFT, there are some topological line defects, or I will call them anions, and they also form a category, a modular tensor category, Z of S, which is the Drinfeld center of S. As I was saying, the Symmetry TFT has 2 boundaries, a symmetry boundary B-sim and a physical boundary B-physio. And the physical boundary on the right is in general non-topological if the theory that we want to study is non-topological, and it contains all the dynamical information about the theory. Well, the symmetry boundary is instead topological, and it's related to the symmetry properties of the theory. In particular, the symmetry boundary has the property that the topological defects that live on it exactly reconstruct the fusion category S that describes the symmetry of my theory. So the idea is that if now I take this interval compactification and I collapse these 2 boundaries together, what I obtain is my theory T, but we on top sort of decorated with the set of topological defects that describe my symmetry S. So this is a sort of way of decoupling my theory and the dynamics from the symmetry properties and abstracting the symmetry properties from the particular theory that I'm studying. And this is usually referred to as the sandwich construction. And let me notice for future reference that I can also consider what it's called the quiche, which is essentially consists of the bulk topological order and the symmetry boundary without putting a physical boundary on the right. So it's like an open Symmetry TFT. Okay, and let me discuss now how we can construct in this picture operators that are charged under the symmetry. So the idea is that also the operators charged under the symmetry are gonna come from this interval compactification. And in particular, they come from some anion Q that is an anion from the bulk, and this is stretched between the two boundaries. So an operator charged under the symmetry comes from the interval compactification of an operator M, which is in general a non-topological end of the anion Q on the physical boundary. And then a topological operator epsilon, which is the end of the anion Q on the symmetry boundary. And as I was saying, some set of topological defects of the bulk, for example, let's say this line S, when projected to the symmetry boundary, has the property that it generates the symmetry S. So the fact that this operator that I get when I collapse the two boundaries is charged under the symmetry ultimately comes from the fact that this anion Q and the anion S that generates the symmetry braid in a non-trivial way in the bulk. So this is why this operator O in the end it's charged under the symmetry S. And in a sense, all the information about about how the operator O transforms under the symmetry is encoded in the anion Q from which it descends in the SymTFT. So we can say in the terminology of this paper here that O transforms in the generalized charge Q. And let me make one remark. The first one is that if there is no such an end on the physical boundary of an anion Q from the bulk, then this means that the charge, this particular charge is not carried by any operator in the two-dimensional theory. And then it could also be that the anion Q doesn't completely terminate on the symmetry boundary, but actually extends as a non-trivial line operator on the symmetry boundary. So in this case, what the sandwich construction would produce is not a genuine local operator, but an operator attached to a symmetry line in the two-dimensional theory. So depending on whether this completely ends on the symmetry boundary or continues as a symmetry line, I get either a genuine operator or a twisted sector operator. Okay. And now, so how do I concretely specify a gapped boundary of the symmetry TFT? So it turns out that a gap boundary can be specified by the maximal set of bulk lines that can terminate on it. And so this is classified by what are called Lagrangian algebras in the Dreamfield Center. So a Lagrangian algebra here is essentially just a sum of a combination of anions in the bulk with some coefficient, which specify which anions can terminate on a boundary. So all the anions that are in L completely end on the symmetry boundary, while the anions that are not in L do not terminate and remain non-trivial topological defects on the boundary. So essentially, while the anions that are in the Lagrangian algebra are completely annihilated on the boundary, those that do not belong to the Lagrangian algebra survive on the symmetry boundary, and they are precisely the topological lines that generate the symmetry. Okay, so we can think of it as imposing Dirichlet or fixed boundary conditions for the anions in the Lagrangian algebra, and imposing Neumann boundary conditions for or fluctuating for the anions that are not in the Lagrangian algebra. Okay. By the way, feel free to interrupt me at any point if you have questions or comments. Okay, so now that we sort of have the SymTFT framework set up, let me tell you how we can use it to characterize gapped phases in 2 dimensions. So the idea is that we want to study gapped phases with symmetry S. So of course, the first step is to start with the fusion category that describes my symmetry and construct the Drinfeld center set of S. Then what we need to do is to classify all possible topological boundary conditions of the SymTFT. And as I explained before, this require us to classify all possible Lagrangian algebras in the Drinfeld center. Okay, and among all of these Lagrangian algebras, there is going to be one particular Lagrangian algebra, which is the one that realizes the symmetry S on the boundary. So the one that precisely corresponds to having a boundary with symmetry S. And since I want to study asymmetric phases, I have to fix the symmetry boundary to be specified by this particular Lagrangian that generates S on the boundary. Okay, and now normally the right boundary, the physical boundary, is non-topological, so it would be totally unrelated to this discussion of Lagrangian algebras. But in this particular instance, we want to study TQFTs. And in this case, then, of course, also the physical boundary is topological, so that when I take the sandwich, I get a 2-dimensional TQFT with symmetry S. So in this case, also the physical boundary is specified by some Lagrangian algebra, which I called L-physio. Okay? And so the idea is that if I now keep LS fixed, which is the Lagrangian algebra that generates the symmetry S on the boundary, and then I cycle through all possible L-phys that I can have, I will span all possible asymmetric TQFTs.
So can I ask some question?
Yeah.
Yeah. Just a clarification. When you have this situation in which also the physical boundary is topological, the symmetry on the physical theory is larger than the one we are discussing, right? Because you have also topological local operators on the boundary.
Right, but so when you do this construction, you have to fix one of the 2 boundaries to be the boundary that specifies the symmetry for you of the theory. So we will take that to be the symmetry boundary. And then when you take the interval compactification, you specify those topological defects to be the one generating the symmetry, while the other boundary will provide for you the order parameters for the gapped phase you want to study.
But so if you start from the physical theory, in some sense, you are arbitrarily choosing a subset of your symmetry that you want to describe with the symmetry TFT. And then there is a quotient which is accidentally described because your theory is gapped.
Well, yeah, I mean, my interest is in studying just a symmetric theory, so you need to make a choice of what you call the symmetry boundary. Then I agree if also the other boundary is gapped, as in this case, there are topological defects living also there. But once you take the sandwich, they are not even mutually local, so you need to specify what you mean by symmetry boundary.
Okay.
Yeah, thanks.
Can I ask a question too, please?
Yeah.
So I'm under the impression that there's certain symmetry categories whose SymTFT is actually an invertible TFT. I don't know, maybe in 2D this only happens with multi-fusion categories, but so for those types of symmetry categories where the SymTFT is actually an invertible theory, so you don't have any topological defects, how does this classification of phases work?
But do you have in mind a particular symmetry S that has such a SymTFT?
Yes, like I know in 3D TFTs with only a billion anyons, I think have this. In 2D, maybe you need to have like Like I think Z2 2D gauge theory may have this, where you have this Z2 one form symmetry and Z2 zero form symmetry, and the order parameter of one symmetry is the defect for the other.
So I'm not completely
Yeah,
sure
if
how
you
it
thought about
works
this.
in a higher dimension, because this is still an open question. This is all in two-dimensional theory with three-dimensional SymTFT. And I don't think what you're mentioning arises in this example. So the SymTFT is always this digraph Witten type theory or Dreamfield Center. I'm not sure.
Okay, yeah,
yeah.
No, I just know like in the in this 2D or sorry 3D case, when you construct the 4D digraph Witten theory and you sum over the background fields, you actually end up getting a trivial theory. So I just figured something like that would happen in the 3D SymTFT case too.
What do you mean 3D boundary or 3D bulk?
3D bulk.
Right. So in this case, it
But
doesn't.
if you haven't thought about it, don't sweat
maybe
it.
discuss
I can
later.
ask you again
Yeah.
later.
Okay. So.
Okay, thanks.
Okay. Yeah. Okay. So the idea is that we fix the symmetry boundary. We change the physical boundary by cycling through all the possible Lagrangian algebras, and this classifies for us 2D gapped phases. And in this setup, we can also define, for example, generalized order parameters. So an order parameter is an operator charged under the symmetry that remains non-trivial, so as a vacuum expectation value in some phase. And if you remember, in the SymTFT setup, charged operators are specified by those anyons that can end on the physical boundary. So in this setting, these order parameters have a charge which is essentially specified by the anion that belong to this Lagrangian algebra L-phys, because those are precise the anions that can terminate on the physical boundary. And then using this setup, we can compute a lot of information about the gapped phase we want to study. For example, the number of vacua is simply given by counting all the anions that can completely terminate on both boundaries, so both on the symmetry and the physical boundary. And then we can also, for example, determine the action of the symmetry on the vacua. And the idea is that in the gapped phase, what the line operators are essentially interfaces between the vacua. So determining the symmetry action requires us to specify every element in every generator of S as some sort of combination of interfaces between the vacua. Okay, and there are, let me mention some interesting features that arise when you look at these classifications, but for non-invertible symmetry, when S is a non-invertible symmetry. So it can happen that so in the usual case, you have either standard local order parameters in vanilla group-like case, or you can also have string-like order parameters. For example, these characterize SPTs. But in the non-invertible symmetry case, we're going to see that standard local order parameters and string-like order parameters are typically mixed together. This is, of course, related to the fact that the non-invertible symmetry action often exchanges local and twisted sector operators. And another feature is that usually when you spontaneously break a vanilla group symmetry, you obtain a set of vacua that, however, are all physically indistinguishable because they are related by the invertible symmetry. While what we observe is that in general, when you spontaneously break a non-invertible symmetry, this can lead to vacua that are distinguishable, so they're not all on equal footing. So let me make all of these a bit more concrete with discussing an example. And as I was saying, the first one is a gapped phase. You focus first on group-like, so gapped phases with Z4 symmetry. And in the cases of group-like, the classification of possible 2D gapped phases is already very well known. And it turns out that 2D gapped phases with symmetry G are classified by a subgroup H of G, and a 2-cocycle alpha in H2 of H with coefficients in U1. So this represents the part of the symmetry which is unbroken in the particular gapped phase. And then we can, this represents a possible SPT that we can put for the preserved subgroup of the symmetry. So this is already very well known, but let me show how we can recover this classification using the Symmetry TFT setup. So the first step is, of course, to construct the Drinfeld center of Z4. And this is just the untwisted digraph-Witten theory based on Z4. So the anyons that live in the Symmetry TFT are characterized by a couple of anyons, electric and magnetic, and both of them are 1 when you raise them to the 4th power. And it turns out that there are 3 Lagrangian algebras in the center of Z4. The first one I call L Dirichlet, and it's just the sum of all the electric anyons, which means that all of the electric lines can terminate on the symmetry boundary. The lines that remain non-trivial are the M lines, and those are the ones that generate the Z4 symmetry. Then I can have another Lagrangian, which I called L Neumann. This is the exact opposite. So all the M anyons can terminate on the boundary, and the E anyons are those that are non-trivial. Those generate the Pontryagin dual symmetry Z4 hat, which is again Z4. And then we can have a third Lagrangian algebra, which I call Neumann Z2. In this case, there is a mixture of E and M anion that can terminate on the symmetry boundary. This would, I call it Neumann Z2 because it corresponds to gauging a subgroup of the Z2 symmetry, a Z2 subgroup of the Z4 symmetry on the boundary. Okay, and since I want to study asymmetric Z4 symmetric phases, I have to fix my reference symmetry boundary, and I choose it to be specified by L Dirichlet. So in all of this discussion, my symmetry boundary will be L Dirichlet, and then I will, we have 3 options for physical boundary that are gonna give us 3 gapped phases. So the first option is to pick also for the physical boundary L Dirichlet. So in this case, we get 4 anyons that can completely terminate on both boundaries. So when I take the interval compactification, this will give for me 4 local operators, V0, V1, V2, V3. And when you compute the symmetry action, I'm calling now P the Z4 generator, so P to the 4th is 1. If you compute the Z4 action on this vacua, you see that these are permuted by the Z4 generator. So we can immediately identify it with a phase where the full Z4 symmetry is spontaneously broken. Then there is another option, which is picking L Neumann as the physical boundary. In this case, only the one trivial anion can completely end on both the Dirichlet and the Neumann boundary. So in this case, I get a single operator, V0, and moreover, this is trivially Z4 symmetric. So this is just the trivial phase with a single gap vacuum, which is just trivial easy for symmetric. And then the remaining option is given by choosing L phase to be L Neumann Z2. And in this case, I have two anyons that can completely terminate on the two boundaries. These are 1 and E squared. And in this case, I get two vacua, V0 and V1. These are permuted by the Z4 action. So we identify this as a phase where the Z2 spontaneous, just a Z2 subgroup of Z4 is spontaneously broken. So if you recall this classification, we exactly reproduced it. So these phases are classified by a subgroup of the Z4 symmetry we're interested in. In this case, this cocycle doesn't arise because it turns out that H2 is trivial for all the possible subgroups that you can have. Okay, and now let me mention how this works with in a non-invertible case. So let's say rep S3 symmetry. And let me denote S3 in this way. So these are the S3 elements where A and A squared are the two cyclic permutations, and BA square B are the three order 2 elements, so the transpositions. And the non-commutativity is encoded in this relation here. And the representation of S3 I will denote in this way. So 1 is the trivial representation, 1 minus is the sign representation, and E is the standard two-dimensional representation of S3. Okay, and now we need to construct the Drinfeld center for the rep S3 symmetry. So since rep S3 and S3 are related by gaugings, their Drinfeld center is the same. And it turns out that the anyons that live in this center are labeled by a conjugacy class and an irreducible representation of the centralizer, Hg, of an arbitrary element in the conjugacy class. So we have first the conjugacy class of the identity. This has, of course, the full S3 as centralizer. And so I get three anyons labeled by irreducible representations of S3, which I call 1, 1 minus, and E. Then we have the A conjugacy class. This contains, this has Z3 centralizer. And so I get three anyons, A1, A omega, and A omega squared, where omega denotes an irrep of Z3. And then I have the B conjugacy class. This has Z2 centralizer. So I get two anyons, B plus and B minus, where plus and minus is for the Z2 representation. And it turns out that these, there are four possible Lagrangian algebras: L Dirichlet, L Neumann Z2, Neumann Z3, and Neumann. And so we expect to get four possible gapped phases with rep S3 symmetry.
Sorry, can I ask a quick question?
Yeah.
S3 is also the semi-direct product of Z3 times Z2. So I would expect that you can construct the different center also starting from diagram with Z3 and then gauging chart conjugation. Is it correct?
You
gauge chart conjugation in the Drinfeld center.
Yeah. You don't gauge the symmetry that switches E and M, but that sends
That's right. Yes. Yeah.
M to minus E minus M, and
this is what I would expect.
Yeah. I think it works.
Okay.
Okay. Thanks. So in particular, the choice of L Dirichlet for the symmetry boundary would realize S3 symmetry on the boundary. Here we want to study rep S3 symmetric phases. So this requires us to specify the symmetry boundary by L Neumann. So if I pick L Neumann as defining my symmetry boundary, This essentially means that the A and the B anyons become trivial on the boundary, and I'm just left with the representation anyons that generate the REPS3 symmetry. Okay, so this is my choice of symmetry boundary. And then I have the 4 options for the physical boundary. So let me start with picking L. Dirichlet as the physical boundary. In this case, again, I'm picking Neumann for the symmetry and Dirichlet for the physical. So there is only the trivial anyon that can end on both boundaries. So this is a phase where with a single vacuum, which is trivially REPS3 symmetric, and I call this the REPS3 trivial phase. Then it turns out that picking Neumann Z2 as the symmetry, as the physical boundary, I get 2 vacua, V0 and V1, which are exchanged by 1 minus, which is the generator of a Z2 subgroup inside the REPS3. So I call this the Z2 SSB phase. By picking Neumann Z3 as physical boundary, I get this phase which I called REPS3, oops, this should be an S3. REPS3 mod Z2 SSB phase, because it turns out that 1 minus acts trivially within each vacuum, but the vacua are exchanged in a non-trivial way by the E generator of REPS3. And finally, as in the previous case, when I pick Neumann for the physical boundary, so I pick the same Lagrangian algebra for symmetry and physical boundary, I get a phase where the full symmetry is spontaneously broken. So in this case, a REPS3 SSB. And the symmetry action in this case is the following. 1 minus leaves V0 invariant and exchanges V1 and V2. While the E generator sends V0 to 2 times V1 plus V2, and V1, V2 into 1 alpha of V0. So there is sort of this symmetry action. And let me mention 2 things that I discussed briefly before, that in this case, we have a non-invertible symmetry, which is spontaneously broken, the REPS3. And notice that indeed V0 and V1 and V2 are distinguishable. Because, for example, this can be seen from the fact that, for example, 1 minus the Z2 symmetry treats them differently. So it singles out V0 from V1 and V2. And this also appears in these factors of 2 in the symmetry action, which we call relative Euler terms. And that essentially appear because in this case, the E line has a non-trivial quantum dimension of 2. And also that the order parameters in this phase, as I was saying, mix together twisted and untwisted sector order parameters. So, for example, if you recall, this is the Lagrangian algebra. So one order parameter is, for example, specified by the anyon A1. And it turns out that this order parameter gives an untwisted sector operator, which are called OA+. But in the same multiplet, there is also an untwisted operator, a twisted sector operator O-, which is attached to a 1 minus line. So the reason why I say that these 2 are in the same multiplet is that the action of the REPS3 symmetry mixes the 2 in a non-trivial way. For example, we see that here the E action on O+ gives also a piece containing O-. And this turns out to be an order parameters for this phase. So there is this non-trivial mixing. Okay, so this was the story for the gapped phases. So let me briefly say what the main point is, that we can study gapped phases which have any fusion category as input, so I discussed these two cases, VecG and RepG, but the symmetry doesn't have to be group theoretical. You can do this for Ising and any fusion category that you like. And essentially, this only requires to construct the Drinfeld center and classify all the possible Lagrangian algebras that you can have in the bulk, and then the gapped phases are classified by all the possible choices for the physical boundary. And then we can compute using this setup all sorts of information on the gapped phase. Okay, so if there are no questions, let me move to now phase transitions. Okay, so now that we have this setup for the gapped phases, what we want to do is to look at possible phase transitions between them. And this requires us to promote the quiche and the sandwich, which I mentioned before, to so-called what we call club quiche and club sandwich. So let me start with the club quiche. And the idea is essentially to just, for both of these, add an additional topological layer in the middle of the standard SymTFT. So we start with our usual symmetry boundary. Then we have the symmetry TFT, Z of S. And then we consider a topological interface to another topological order Z prime. So in the SymTFT spirit, this is a setup to study, if you want, asymmetric boundary conditions of a different topological order Z prime. So concretely, this gapped interface is specified by a condensed. Sorry, my pointer doesn't work anymore. Okay. So concretely, this interface is specified by what is called a condensable algebra in the Drinfeld center. So the idea is that if you take an algebra and this algebra is Lagrangian, so of the kind that I discussed before, all the anyons that are not in A braid in a non-trivial way with at least one anion in Z of S. And this means that when you condense A and you take this quotient, the reduced topological order is trivial because everything braids non-trivially with the thing you're condensing. But if A is not Lagrangian, so it's not maximal, there are anyons in Z of S that still braid trivially with all the anyons in the algebra. So when you take this quotient, you get reduced topological order, Z of S prime, where in general S prime is a smaller symmetry, a smaller fusion category than S. So this is our setup. We start with a symmetry boundary. Then we have the Drinfeld center, our gapped interface, which is specified by the condensed algebra, and then our reduced topological order. And then we notice that we can consider holding this picture along this gapped interface. And then I get, what I get here is this topological order, Z of S time Z of S prime bar, where this just denotes the reflection of Z of S prime. And then I get an interface to just the trivial theory. So this is to say that this gapped interface specified by a condensable algebra can also be rephrased in terms of a Lagrangian algebra in this folded topological order. And of course, my original condensable algebra A must be a subset of this Lagrangian algebra that defines the boundary. Okay.
Sorry, I think I don't understand this picture. You're discussing the quiche, right?
Yeah.
So in the top picture on the right, it's infinite. You're not choosing
Yes.
a boundary. So when you fold
No.
on the left, it should become infinite.
Yeah. So this boundary becomes this, and this continues infinitely in the trivial topological order, if you want. So I'm just folding this part on top of this.
Yeah, but the part you are folding is a non-trivial TFT. You are putting it on the left.
Yeah. Yeah.
So why on the left at some point it ends on the B symmetric? I would say that on the left of B symmetric, there is still Z of S prime. Unless you add an additional topological boundary on the S prime to make it terminate.
Right, but it turns out that so this is a reduced topological order, and all the things that terminate here are so what do I want to say? Basically, this is also a boundary for Z of S prime, because S prime is a smaller symmetry. So
Okay.
no inconsistent, like you don't get things that don't terminate or such, because everything here is connected here, and things at an end, and things there is a non-trivial map between each anion here and each anion here. So this defines a consistent boundary condition also for the topological order.
Okay,
Just
basically
the fact
maybe
that it's always a subset. Yeah.
okay, maybe what you're doing is that the B symmetric, which is a boundary of ZS, induces another boundary for ZS prime. So on the top picture, I have to think that I make the right also to terminate on another boundary, then I fold and I get the bottom picture, right?
Yeah, if you want,
Okay.
yeah.
Okay.
But I will discuss an example of Klapkish, which hopefully it will make clear what this picture is. Okay, and let me tell you that. So again, in the special case where this condensable algebra is actually Lagrangian, then this Z of S prime is trivial. So this whole business collapses to the classification of to the classification of asymmetric gap phases, which I mentioned before. Okay, and now let's see this in the Z4 example. I'm sorry if these slides becomes a bit technical and ugly, but I'll try to show the main points. And in this case, it turns out that, for example, a condensable algebra is this one. So 1 plus the E square anion. And if you compute the reduced topological order, so Z4 mod this condensable algebra, it turns out to be the toric code. So the center of Z2. And I denote it by, in the standard way, by 1, E, M, and F. And I put primes here to distinguish the toric code anions from the original Z4 anions. And this Lagrangian 1 plus E square, this algebra 1 plus E square in Z4 can be equivalently expressed as this Lagrangian algebra in Z4 times Z2 topological order. Anion in the original Z4 is, I'm in particular interested in the anions that can terminate on the Z4 boundary, which, if you remember, those are the E anions. 1 plus E square, just go to the identity. So I get that E square can terminate on this topological interface, while both E and E cubed are mapped to prime. So they don't end here, but they continue being E prime in the reduced topological order. And now what I want to do is to collapse these two boundaries. And if you do it, you get a boundary of toric code where now two E prime anions can terminate. So This tells us that this boundary here, it's not an irreducible boundary of toric code, but it's actually the sum of two electric boundaries of toric code. And in particular, I can rearrange these operators that I get into these bases, again, V0, V1 of idempotence. And so these are supposed to be the identity on V0, the identity on V1, and these E0, E1 are the ends of these E prime anyons respectively on the two boundaries. Okay, and now I can ask, what are the line operators that should live on this reducible boundary of the toric code? Those are these, I call them 1 and eta, with these indices that can be 0 or 1. And 1, 0, 0 and 1, 1, 1 are simply the identity line on these two boundaries. Then I have eta, which is just the Z2 line. Eta 0, 0 and eta 1, 1 is simply going to be the Z2 line on each boundary. But then I can also have lines that interpolate, are interfaces between the two boundaries. These are going to be 1, 0, 1 and 1, 1, 0, and similarly for eta. And now specifying the symmetry, so what we want to do is specify how the Z4 original Z4 symmetry is mapped to these lines that are the lines on this B prime boundary. So this can be, we can know this if we know how the Z4 generator P acts on this identity and E prime anyons on the boundary. And it turns out that P switches V0 and V1, and it sends E0 to E1 and E1 to minus E0. So in this case, we can identify the Z4 generator as the line 101, so that sends E0 to E1, and eta 10, because E1 is sent to E0 with a minus sign. And notice in particular that P square instead is just, it doesn't act by switching the two boundary, but it remains localized within each boundary. So it's just the Z2 element within each boundary. Okay, you can, for example, do the same for RepS3. In this case, there is one choice of condensable algebra is this one, 1 plus A1. And it turns out that also in this case, the reduced topological order is simply the toric code. So again, I have the center of RepS3 and then the toric code. This case is a bit different because the boundary that I get, it's again reducible, B prime, but it turns out that it's a sum of an electric boundary and a magnetic boundary because I have an E anion and an M anion terminating on it. And now if I ask which operators live on B prime, they are similar to the ones I discussed before, but the line that interpolates between these two electric and magnetic boundary is this Curlian line that actually has sort of Kramer's one-year fusions, so non-invertible fusions. This is due to the fact that I can think of the magnetic boundary as the Z2 gauged version of the electric boundary. So actually this interface between the two boundaries is like an interface where you gauge Z2 in half of the space. Okay, and again, I can identify the symmetry generators of RepS3, which are 1 minus and E, as some suitable combination of these lines living on the B prime boundary. Okay, and now let me finally move to phase transitions. So to this club sandwich that we consider. And the idea is that, okay, the club sandwich is simply given by slotting a physical boundary condition to the right of the club quiche. So now the setup is, again, we have symmetry boundary, we have the Dreamforce center, the condensable algebra, the reduced topological order, and then we put a physical boundary condition. And now if I would take just the sandwich here, in the standard SymTFT picture, this would produce for me an S prime symmetric theory, which I call T prime of S prime. But if you now take this full sandwich here, this produces for you an S-symmetric theory. So concretely, what we want to think of this club sandwich is a machinery that can map for us an S prime symmetric theory to an S symmetric theory. And in particular, we want to apply these to phase transitions. So the input is, let's say that I know a CFT, C of S prime, and I know that this CFT sits at the transition between two S prime symmetric phases. So it sits at the transition between an S prime symmetric phase 1 and an S prime symmetric phase 2. And the idea is that if I now pick as physical boundary condition in my club sandwich, the one corresponding to this CFT, the club sandwich will produce for me now an asymmetric CFT that now sits at the transition between two asymmetric gapped phases. Okay. So let me mention it in the Z4. Let me describe this in the Z4 example again.
Sorry, quick
So-
question.
Yeah.
Why are you assuming the phase transition in second order?
I'm just considering particular cases of CFT that I know are inputting between two gapped phases.
But I
This
think that
is
your
a second
machinery could
order-
work for any phase transition. First order, second order, whatever. It's
Right,
not
but
necessary to assume that you have a CFT.
Right, but here literally the input is that you start from an S prime symmetric CFT. That
Yeah, I understand. I'm asking
second
why you're
order
putting
difference.
this input. Is there something special that you have in mind, or why don't you discuss just generically phase transition between two different theories with different symmetries?
Because so in this setup, what you can do is so the goal is not to find out, let's say, what's the phase transition at two generic gapped phases. So what this setup can do for you is that once you know some S prime phase transition, then you can input it in the club sandwich and you will generate a phase transition for a larger symmetry S. So what we sort of want to do here is start with a minimal phase transition that we know already and feed it into the club sandwich formalism to generate larger phase transitions. So this is the setup. We are not discussing we're not answering the question, what's the CFT or what's the theory living at two completely arbitrary gapped phases. But
Okay, but even if your
it's true that in this setup, in principle, you can input any theory that you know sit at the phase transition.
Okay, good, okay.
I'm in particular gonna focus on gapless in here, but yes. Okay. So let me discuss Z4 again, the Z4 example. Again, we have Z4 symmetry, and we are still working with this condensable algebra, 1 plus E square. And if you remember, the reduced topological order is Z2, so S prime is equal to Z2. And of course, the original S is Z4. So in this case, we want to see the Klapkisch as a map from a Z2 symmetric theory to a Z4 symmetric theory. And the boundary, if you remember the Klapkisch, the boundary B prime decomposed in two copies, B0 and B1 of the electric boundary. So in this case, my Z4 symmetric theory is essentially given by two copies of the S-prime symmetric theory. And this was the form of the Z4 generator P. So the generator of Z4 acts by switching these two copies of the S-prime symmetric theories, while this was the form of the of P square, so the generator of the Z2 subgroup. So this Z2 inside Z4 is identified with the diagonal Z2. So essentially, this is the structure of my S-symmetric Z4 symmetric theory. It's given by two copies of the Z2 symmetric theory, and the Z4 acts by switching them, while P square just acts within each universe. Okay, and now let's discuss the phase transition. As I was saying, I need to input an S-prime symmetric CFT, which I know sits at some phase transition. So in this case, we can choose the Ising CFT, which is Z2 symmetric. And we know that Ising CFT admits two deformations by the energy operator, one that gives us the Z2 spontaneously broken phase, and one that gives us the Z2 trivial phase. So recall that this was the Lagrangian algebra that corresponded to the condensable algebra 1 plus E square in the center of Z4. So this tells us what's the map of anyons between Z4 and Z2. So in particular, 1 goes in 1 plus E square, E prime goes E plus E cubed, etc. And now the idea is that I'm studying the Ising CFT, which is at the transition between Z2 SSB and Z2 trivial. So let me start with the Z2 spontaneously broken one. In our gapped phase classification, this corresponds to picking 1 plus E square and 1 plus E square, so that I get two vacua and the Z2 spontaneously broken phase. So if I now take 1 plus E prime and I apply to it this map, I get this Lagrangian algebra. Okay, and if you recall from the gapped phases discussion, this is precisely the Lagrangian algebra that corresponds to having the full Z4 symmetry spontaneously broken. And now let's discuss the second one, which is the Z2 trivial phase. This would correspond to picking as physical boundary 1 plus M prime. So it's specified by this Lagrangian algebra, so that I just get a single vacuum. And if I complete 1 plus M prime, I get this Lagrangian in Z4. And again, this is the one that corresponded to the Z2 spontaneously broken phase. So what I want to say is that the Ising CFT that sits at the transition between Z2 SSB and Z2 trivial is now uplifted to a CFT that sits at the transition between Z4 spontaneously broken and Z2 spontaneously broken phase. And notice that we could have also seen this from the fact that the condensable algebra 1 plus E square is precisely the Lagrangian that is given by the intersection of these two Lagrangian corresponding to these gapped phases. So this in the group setting was discussed in this paper by Chatterjee and one that I mentioned at the beginning that has a similar setup. Okay, so and now I simply put the Ising CFT here. And what I get is that now the CFT that sits at the transition between Z4 SSB and Z2 SSB is given by two copies of Ising that are essentially permuted by the Z4 generator. And now you see that if I deform this by this operator, each of the single copy of Ising would collapse to the trivial phase. So I get two vacua. And this is the Z2, but the two vacua are still permuted by the Z4 generator. So this is still a Z2 SSB. And instead, if I do the opposite deformation, then each of the two copies of Ising gives me a spontaneously broken C2. So in total, I get 4 vacua, and these are all permuted by the Z4. So I get the Z4 spontaneously broken phase. So we uplifted the Ising CFT to this sort of weird looking CFT that it's now at the transition between C4 SSB and Z2 SSB. And in a way, you can think of it as being the Ising CFT, but with a topological theory stacked on top of it. So it's like being Ising with a Z2 spontaneous breaking stacked on top of it. Okay. Now I'm out of time, so let me not go into details about the RAPS3, but if you do the same, you can also discuss the RAPS3 phase transition corresponding to this Lagrangian algebra that we discussed before. It turns out that this is a transition between the phase where the RAPS3 symmetry is fully spontaneously broken and the phase where all RAPS3 except for the Z2 is spontaneously broken. So again, this is in a sense a transition that spontaneously breaks a Z2. And so again, the CFT in this case is some complicated multi-copy of the Ising CFT. Okay, and so to summarize, we have seen how we can use the SymTFT framework to study phases in 2 dimensions, both gapped and gapless. And this is a setup that can take an infusion category as input, and that allows us to compute concrete information. And moreover, this generalization to club quiches and club sandwiches, that it's useful to study phase transitions. So there are a lot of generalizations for in which one could extend this. Of course, the first one is to extend this setup to higher dimensions, because a lot of the so extend this to higher dimensions, and this would require to know more about SymTFT and dreamfield centers in higher dimensions. And another direction is to consider interfaces in this club quiche and sandwich picture that don't correspond to phase transitions, but to more exotic gapless phases, for example, GSPTs. So I think this is something Sakura, Laksha, and Dan are working on now. Okay, so thanks a lot for the attention, and that's it.
So thank you, Lea, for the nice talk. If there are any questions, please feel free to unmute yourself and ask directly. So maybe I can start with a question. So in the Z4 quiche, club sandwich example that you gave, you only see transition between Z4 broken and Z2 broken phases, right?
Yeah.
I guess if you change the algebra, then you'll see a transition between Z2 and fully broken. Sorry, Z2 and Z4 symmetric phase.
Yeah, exactly. So this is the one that I discussed was very specific to this choice of condensable algebra, but there are other condensable algebras in the center of Z4, and you expect that each one of them would give you then a transition between different phases. Yes.
But always Z2 symmetry breaking transitions.
I think in our setup, yes.
I see.
Yeah, so you can get the Z2 spontaneously broken phase to the just trivial Z4 symmetric phase by changing the condensable algebra. Yes.
I see, and of course, you don't find the Z4 spontaneous symmetry breaking transition as a direct transition because that won't come
No,
from.
because that would yeah, that's already like the minimal one that we are instead inputting in this picture. Yeah.
I see. Yeah, Orko, you can
Hi,
just.
yeah, thank you. Hi, thanks for the talk. I had a question about this comment you made about gapless versus first order. So in your setup, is there a way to distinguish multi-critical versus critical gapless transitions where you have like more than one relevant operator at the CFT versus only one?
Right. Yeah, so I think this would so this discussion about the fact that, for example, in this case, we have this particular just a second. So we have this particular condensable algebra AE. This is specified by the intersection of the Lagrangian corresponding to the Z4 SSB and the Lagrangian corresponding to the Z2 SSB. And so we argue that this AE corresponds to this phase transition. But you could also consider Lagrangian condensable algebras that sits at the intersection between more than two Lagrangian algebras. And so I would expect that in that case, you get a multi-critical point.
Oh, okay. Thanks.
Thank you.
Any more questions? So if not, let's thank Lea again, and maybe we can stop the recording.